now Hicham will give us an introduction to GPUs. You can, yeah, if you want to introduce yourself.
Yes, well, my name is Hicham, so I'm working in scientific computing at UAB. So in this presentation, we will go a little bit outside software installation and introduce you a little bit to GPU accelerators. As you know, today GPUs, they are integrated in supercomputers, which means that they offer really possibilities of addressing many fields in HPC and AI and data analytics. So this is something becomes very important in order to solve some complicated scientific problems which wouldn't be possible really in conventional clusters or conventional supercomputers that are based on only CPUs. So I'm listing here some of the examples that supercomputers with the GPUs would have the capability really of addressing and the things that wouldn't be possible decades ago. So this is the example of exploring the boundaries of quantum chemistry and predicting, for instance, the structure of proteins that wouldn't be possible without the presence of GPUs. And this goes to natural language processing models, where a large set of data to be trained requires really GPU accelerators. So this really shows the power of GPUs in order really to address some large scientific problem. So therefore, the idea here behind this presentation is really not to address the technical aspect of GPU programming, but rather really to initiate your interest in using GPUs. So that's why the outline of my talk will be split in different parts. So in the first part, I will talk a bit about the hardware topology. So we compare CPU versus GPUs. So then a little bit about how to map parallelism into GPU accelerators. And then shortly about a GPU direct technology, which enables really to gain performance, especially when the application runs on multiple GPUs across multiple nodes. And at the end, there will be a short hands-on. This is just you to experiment yourself. We will have a mini application that you will run it on a GPU, and you will run it on a single CPU, and then you evaluate yourself the performance that can be gained by using GPUs. So that's the general outline of this presentation. So before I start, I want to inform you about this upcoming event. If you are interested in GPU programming, so this will be on the 9th and 12th of June. So the event will cover different GPU programming models, and it's kind of collaboration between different institutes in Sweden, Finland, and also in Norway. So I definitely recommend to register for this event if you are interested in learning about different GPU programming. And I think at the end it will enable you to choose the right model that might fit in for your application. So okay, in the first part, we'll cover basically 3 elements. So the first element, just to define some terms that are widely used in HPC community, heterogeneous system. So a bit about how to measure the performance of a processor, and then I will dive a little bit in the CPU and the GPU architectures, then to get some understanding, some basic understanding of these two architectures, which are necessary if you are doing code development. Heterogeneous system in general is a system that is composed of different type of hardware and software which are interconnected. And this is the case with with the CPU and the GPU. So a system that has a CPU and the GPU, probably other accelerator, are considered as termed as a heterogeneous system. And this is, it goes from a server, a single node, to clusters which are suitable for small scale computations, as they contain up to hundreds of thousands of clusters, and to supercomputers which are suitable for large scale computations. So heterogeneous system is a general term that is widely used in HPC community, and it refers really to the use of different hardware and software. So the advantage that this heterogeneous system it offers is really, it permits to increase the performance and scalability. It increases really the performance compared to traditional HPC systems that are based only on a CPU. And speaking about the performance of a processor, so the way performance of a computer is measured is based on this quantity called flops, floating points of operations per second. So this quantity measures the speed of a computer to perform arithmetic operations, and is given by this quantity. So flops, it's you have the clock speed, which is given in gigahertz, you have the number of cores, and then you have the precision of the computing. So here we shouldn't confuse flops with small s per cycle and flops with big S. So the small s here, it refers just to the player, and flops here is just a way of encoding a real number. It can be a simple precision, double precision, or half precision. So now if we consider a situation where we fix the clock speed and we fix the precision of the computing, and we vary the number of cores, what you realize is that the performance will increase linearly with increasing the number of cores. And this is the case, for instance, if we compare the performance of two processors. Let's assume we have the processor one which has 10,000 of cores, and a processor two which has 100 of cores. So obviously one can see that the processor that has 10,000 cores will offer performance that is up to 100 times larger than processor one. So here we basically talk about, for the processor one, we talk about the GPU, and for the processor two, we are talking about the CPU. So since we are talking about CPU and GPU, let's start by talking diving a little bit into CPU architectures. So this is a picture of a dual socket Intel CPU. As you can see, it has two CPUs, CPU1 and CPU2. So each CPU has a main memory. So if we focus a little bit on the CPU1, what you see is that the CPU has consists of many CPU cores. So each CPU core has its own L1 cache memory, L2 cache memory, and all the CPU cores, they share the L3 cache memory. Now the difference here is that L3 cache memory is larger than L2 is larger than L3, L1. In other way, the data can be accessed very fast from the memory L1 and slow a little bit in L2 and become slower to the main memory. So this access of memory is that what causes a problem of memory latency, which means when a processor asks look for a data, the first thing is that it checks if the data are stored in L1, and then check if not, it will check if it's stored in L2, and so on. So, and this things takes really time making the use of this of a CPU if the code is not well designed to cause a large waiting time, which is the case for the CPU for the CPUs in general. So one of the issues here with the CPU is really related to high memory latency, which reduces the overall system performance. So and this is the case really when a code is poorly developed, which means it doesn't respect the management of the memory or lack of knowledge of memory hierarchy. It creates this issue with high memory latency, and even if the code is run on the most powerful supercomputers in the world, it will not get any benefits. So this is an important point that users basically needs to know, or to get an overview of the CPU architecture. It helps really designing code in an optimal way. So now let's move to the GPU architecture. The widely used GPU architectures, we have AMD and NVIDIA. They are widely used in the scientific community. So in this presentation, I will be mostly focusing on NVIDIA GPU, simply because our clusters are based on NVIDIA, and the second is that the many applications that we will be running will be on NVIDIA application. So now, if we look at the architecture of the NVIDIA GPU, we basically, there are too much information. It's difficult to reveal or to the main component of the GPU architecture. So that's why I decided to provide a very simplified representation of the GPU, which I believe contains the main component that would help us to understand in somehow the architecture. So I consider here the representation of the GPU here. As you see, the GPU consists of streaming multiple processor, SM. So multiple streaming multiprocess, they share L2 cache, and this is important to know to know that how many multiprocessors they share L2 cache depends on the GPU model. If I look at the AI A100 GPU, they have 108 streaming multiprocessor, and each streaming multiprocessor contains 64 cores. In this model, 32 streaming multiprocessors share the same L2 cache. So this is, it gives you just an idea about the hardware characteristics of the GPU in terms of the amount of core it contains. So, okay, if we go back again to this picture. So each streaming multiprocessor consists of multiple cores. So all the cores here, they share the same L1 cache memory, but each core has its own private registers where the data are stored temporarily during the computation. And here each core consists of arithmetic logic unit. This arithmetic logic unit, they are responsible of making various logical operations, either simple precision, double precision, or integer. They carry operations such that multiplication, addition, and so on. So the particularity really here of the GPUs is that the stream multiprocessors have these features to execute multiple threads simultaneously, which is not the case in a CPU. So because of these features, GPUs, they can really handle large amount of data in parallel, which means they can do a lot of work in a short time scale compared to the CPU. So if we want to summarize the differences between the CPU and the GPU, so I gather here these two pictures that facilitates our understanding of the basic features or basic differences between a CPU and a GPU. So if we look at the CPU, a CPU has 100 of CPU cores. While if you look at the GPU has about thousands and even 10,000s of cores, depends on which GPU models. So here for the CPU, each CPU core has its own cache memory. While for the GPU, so multiple cores, they share L1 cache memory. So once again, because each core has its own memory, threads on a CPU execute independently of each other. While on the GPU, threads are organized into blocks of threads, and this enable to execute multiple tasks in parallel. So what you get from here is that the CPU, based on these features, is that CPUs, they are more suitable for small scale parallelism with a few threads, while the GPUs, they are more suitable for massive parallelism with thousands of threads that they are executed. They are executing tasks in parallel. So the main conclusion that can be taken from this comparison is that GPUs, they are designed for high throughput, which means to carry a large amount of work in a given period of time. Another thing is because the way the memory management is designed, it helps to reduce latency. So because of these two features, GPUs, they are considered to be powerful, really, for handling a large amount of work in a really short time scale. So so let's move a little bit now to briefly talk about how the parallelism is mapped into the GPU. So in this part, I will be covering shortly different GPU programming models available, and then we'll take an example of OpenECC to discuss a little bit how the parallelism is done and how the parallelism is mapped into the GPU. So here I'm listing different programming models. I'm classifying them according to high level and low level, or directive-based model. So OpenECC, we have OpenECC, SQL, and OpenMP. So these models are considered as directive-based model, and we have CUDA, OpenCL, and HEAP, which are low-level models. So the difference between these models depends really on the hardware. So for instance, a GPU, an OpenECC model has support on NVIDIA, but only OpenECC Fortran is supported by AMD. So on the other hand, SQL is a cross-platform model, which means it has support on NVIDIA, AMD, and also Intel. When it comes to CUDA, of course, is supported by AMD, by NVIDIA. CUDA, AMD does not support CUDA. OpenCL is also a cross-platform model. It is supported by NVIDIA, by AMD, and Intel. And then we have HEAP. It's a model that is supported by AMD and also by NVIDIA. So this means that if your application is written in CUDA, it will run on NVIDIA, but it will not run on AMD. So therefore, you need the application needs to be ported to AMD. And there are some automatic tools to port applications from CUDA to AMD, and the same, there are tools that permits to port application from OpenECC application to OpenMP, such that it can run on an AMD GPU-based machine. So this GPU model also can be combined with MPI, for instance, and OpenMP threading. So then which offers the possibility of incorporating GPU models into existing MPI applications or OpenMP applications. So now in the next, what I'm going to do, I will try to take the OpenECC model and explain to you shortly how the parallelism is done in for this model. So OpenECC first is a directive-based model, as I mentioned, and it's also an application programming interface that enables communicating between CPU and the GPU in a very simple way. So now when you compile, now how the parallelism is done is when you compile an OpenECC application, what happened is that the compiler will generate a block of threads. So as you can see, as schematically presented in this picture, so it generates a block of threads. So then the kernels so will transfer the data to the GPU, and the data will get executed redundantly on each of these gang or all gang, also called block of threads or CUDA block. So the data will be executed redundantly on each of these block of threads. So then a block of threads will execute the same instruction, but on a different piece of data in parallel. So on each part here, so the block of thread will execute a different piece than here, but all will run, will be executed in parallel. And that's what it refers to as SIMD, single instructions, multiple data. It processes multiple data with the same instruction in parallel. And that's what makes the particularity of parallelism on GPU. So this picture, it shows how a software aspect is mapped into the hardware. A CUDA thread or a full warp, that's a term is used also in the GPU community. So is executed on a CUDA core. And then a CUDA block or block of threads is executed simultaneously on a streaming multiprocessor. And then a grid of CUDA block is executed on the GPU device. So it shows you a picture about how somehow the parallelism can be mapped in the GPU in terms of threads and in terms of the hardware unit, which are here the CUDA core. So so this is about the parallelism in OpenECC. I want now to move and tell you a little bit about a technology that is developed by NVIDIA, which is called GPU direct technology. So this technology is based on a mechanism called direct memory access. So this mechanism is basically used to transfer data between an I/O device and the GPU memory. So the I/O device here, it can be a storage device, a network interface card, and the GPU memory. But the most important, the key features of this technology is that there is no involvement of the CPU. So the transfer of data, it goes directly from, for instance, from a storage device directly to the GPU memory without the involvement of the CPU. So in this case, we talk about GPU direct storage. So the data are transferred from a storage device directly to the GPU memory. So there's no involvement of the CPU, and even the kernel is not constantly involved there. The kernel, they need to initiate the transfer, of course. So another technology is called GPU direct RDMA, GPU direct remote direct memory access. So this is an interesting technology that enables communication between two GPUs sitting on two different nodes, such that nodes they are connected either via InfiniBand or a slingshot in other HPC system. So in the following, I will focus a bit on this technology, GPU direct remote direct memory access. So you can see it very clearly here in this picture. So on the left side, I have node 0, which consists of a CPU and 4 GPUs. On the right side, I have another node, node 1, consists also of 4 GPUs and a CPU. So this when this technology is enabled, so the data will be transferred directly, for instance, from the GPU1, from the GPU memory to the GPU memory of another node, without involvement of the CPU, and also the use of the kernels is just to initiate the transfer. So this technology is really important to reduce the communication latency and, of course, improve the performance. So before I will go a little bit more in details in this technology, let's look at the traditional way of communication between two nodes. So that's basically when the data are transferred between a CPU and the GPU. If we assume that the data are already present in the GPU, so the kernel is needed to transfer the data to the CPU. The CPU has to do some operation and retrieve the data from the CPU memory, and then transfer the data through the network to another node. The same to the CPU. The CPU has to do some operation with the involvement of the host memory, and then transfer the data to the GPU. So the GPU does some kernels that makes use also of this GPU memory. So you can see here that the path to communicate between a GPU in this node and the GPU in this node is really long, and that leads to high latency. So this GPU direct technology, it comes really to increase the performance, which you can see, which you can notice in this picture. So if the GPU direct remote direct memory access is enabled, so what happened is that if we assume that the data are present in the GPU, so the data will be directly goes from the GPU memory to the network interface cards, and you can see there is no involvement of the kernel, as I said, except if to initiate the transfer, and then the data will be transferred from the network card of the node 0 to the network card of the node 1. Note that the speed here, it's about 200. It depends on the network, but for HDR InfiniBand, it can be up to 200 gigabyte per second. So this network interface card, they are considered as protocol staging, which means they are not meant for general purpose computing. So they are staging protocol that they can so the data are staged here and then transferred back to the GPU memory on the other node. So this technology, it really taking into consideration the network. It really, it really helps reducing communication latency and improving the performance. So just to conclude about what we have seen. So in short, the features that the features of the GPU architecture is illustrate really the powerful of the use of the GPU for really massive for a massive parallelism, and we can see that in the last six years there has been really an increased interest in developing GPU hardware, and you can see that from this table. From 2016 to 2020, the number of cores has increased by a factor of 5. So it goes from 3,000, almost 3,600, the number of cores for P100, to almost 18,500 for the new GPU model. And then when you look at the peak performance, it goes from 9.3 teraflops to almost 77 teraflops. So the peak performance has increased by almost a factor of 7. So this is really, it shows that the fast progress of developing high performance hardware, which in parallel has enabled some scientific breakthrough. And the example here is AlphaFold, which has enabled really to construct the structure of proteins in a fast way and a simple way. So this is really an example that shows the power of using the GPU that wouldn't be really possible with the conventional supercomputers that based only on a CPU. So that's really what I have to say about the GPU. So now, if you want, we can have a demonstration. We have a mini application that we can experiment with to see really the power of using a GPU. To do that, I have prepared a small little exercises here. So in which you will run a code that is written in a serial form, and then you will run the same code that is GPU accelerated, and then you can evaluate the time it takes to run each code. So the exercise is the steps to follow are listed here, and they can be found also in the README file text in this directory GPU exercise. So I will just give you 5-10 minutes. Then you can run this run this application, and we can come back again. But if you have any question, I can take questions while you are running this mini application. Okay. Can you see my screen, right? You can see 2 terminals, right?
Yes.
Yeah. Okay. The exercise here, there are 2 codes. As I said, one is written in a serial form that run only on a single CPU core, and the other code is the same code, but it's accelerated with OpenECC. So we will basically just follow the steps and try to run the serial code and run the accelerated code, and then try to evaluate the time it takes for each of these codes. So simply you can copy the folder to your local path, to your local to your path, and then we will start with the serial code. I will just compile the code, and then I will run it interactively. Is interactive.
I think
So
maybe you're sharing a different terminal because we don't see anything.
Oh, that's okay. Let's see. Yeah. Can you see it now?
I see your terminal, but I don't see you're doing anything in it.
Oh,
Maybe you're in a different.
Yeah, different. Okay, we go to the.
No, I see it. Okay.
Can you see it now? Yeah. So okay, as I said, I compile the serial code, and then I run it interactively here. So this it will take some time. Then I can run the executable. So probably it might take about 100 seconds. So I cannot show two terminals at the same time, right? It seems like. The code basically what does is it solves 2D Laplace equation. So it starts with some initial conditions and iterates over those conditions until it's converged with an error that is defined here to be less than 0.05. Yeah, so you can see that the serial code, it takes about 103 seconds. So now if we try to accelerate this, to run an accelerated code, it's located at the folder accelerated code. So I will compile. So the compiler here, you can see, just to show you what is in the compile file. So I'm simply loading an NVHPC module, and then compile with NVFortran. And you have some options here, ECC, to enable the accelerating with OpenECC. So if I compile, you can get a message output that it shows what the compiler does. So you will see there is a warning here, but you shouldn't worry about that. So next, I run on a single GPU. It seems, yes. And then it allocates the node C71, which has a GPU. So then I can run the executable. So what you can see that the GPU here, the same code, it takes 1 second on a GPU compared to 103. So you can see that you can gain a factor of 100 by running a simple mini application. So this is just an example. It shows how fast running or using a GPUs. Of course, how much performance you will gain depends on how the application is designed. And of course, there are some cases where the use of GPU might not be switchable. And this is the case if the application involves transferring data between the CPU and the GPU in a systematic manner. So that's one of the bottlenecks in using GPUs. But if the GPUs are used, the data are transferred in the GPUs, and the data stays in the GPU as long as possible, then this is the switchable case where the use of GPUs are beneficial. So so this is what I wanted. This is the exercise that I have for you. But if you have any questions or any. Yeah.
I don't see any questions yet, but yeah, keep them coming if there is any.
Another thing I want to use for those who are running distributed deep learning or developing their own code and are interested in accelerating their application, they can just contact us. So because this is the service that we provide within NRIS. So we assist users in accelerating their applications, but also we assist users in making the transition from small clusters to big supercomputers. So if you are interested in one of these things, just let us know and we can have a chat.